Hello everyone, a warm welcome to all of you. Thank you for joining us. This one is the final session of our 3-day international webinar on emerging trends in computational technologies, IWETCT, organized by the Department of Computer Science and Applications, University of North Bengal, in collaboration with IEEE CIS Kolkata chapter and Computer Society of India, Shiliguri chapter. For our final session, we are pleased to have Professor Amlan Chakrabarti, Professor and Director of A.K. Choudhury School of IT, University of Calcutta. Professor Amlan Chakrabarti is a full-time professor in the A.K. Choudhury School of Information Technology at the University of Calcutta and the former Dean, Faculty of Engineering and Technology from 2016 to 2019 of his university. He is also heading the IT and Technology Innovation Cell of the Department of Higher Education, Government of West Bengal. He is an M.Tech from University of Calcutta and did his doctoral research at Indian Statistical Institute, Kolkata. He was a postdoctoral fellow at the School of Engineering, Princeton University, USA during 2011 to 2012. He has almost 20 years of experience in engineering, education, and research. He has also served in various capacities in various higher education organizations, both at national and international levels. He is the recipient of prestigious DST Boy Scout Fellowship Award in Engineering Sciences 2011, Indian National Science Academy INSA Visiting Faculty Fellowship 2014, JSPS Invitation Research Award 2016 from Japan, Erasmus Mundus Leaders Award from European Union 2017, Hamid Visiting Professorship from University of Cambridge, UK 2018, Shiksha Ratna Award by Department of Higher Education, Government of West Bengal 2018, and IBM Quantum Researchers Program Access Award 2021. He has also served in various capacities in various higher educational organizations, both at national and international levels. He has received multiple project grants in the areas of security in cyber physical systems, IoT, embedded system designs, VLSI design, quantum computing, computer vision, and data science from various national and international agencies like DST, DRDO, NIET, UGC, DAE, Ministry of Social Empowerment, the West Bengal DST, Intel India, TCS, etc. He has contributed immensely in the development of intelligent algorithms and systems to support real-time applications, cybersecurity, quantum computing, healthcare, environment, and water quality, etc. He was the principal investigator of the Center of Excellence in Systems Biology and Biomedical Engineering, University of Calcutta, funded by MHRD under TechIP3 funding during 2013 to 2017. Till date, he has graduated 16 PhD students. He has published around 180 plus research articles in referred journals and conferences. He is a senior member of IEEE and ACM, IEEE Computer Society Distinguished Visitor since 2020 to 2022, Distinguished Speaker of ACM from 2017 to 2020, Vice Chair of IEEE CEDA India Chapter, Vice President of Society for Data Science, and life member of CSI India. He is the series editor of Springer Transactions on Computer Systems and Networks, associate editor of Elsevier Journal of Computers and Electrical Engineering, and guest editor of Springer Journal of Applied Sciences. His areas of interest are machine learning, computer vision, cyber physical systems, quantum computing, and VLSI CAD. I would request Professor Chakrabarti to start his presentation or invited talk now onwards.
Okay. Yeah. Thanks. Thanks, Dr. Millie, for this brief introduction, and thanks to the organizing committee of the Department of Computer Application, North Bengal University. And I hope that all the participants have enjoyed great lectures in the previous sessions to mine, and I am also so lucky to give that the last to give my lecture, offer my lecture at the last session of this wonderful workshop. Okay. So I feel I'm audible to all of you, right?
Yes, sir. Yes,
okay. Sir. So let me start my presentation. And as you know, I think all of you know that my today's topic is pretty exciting in the present domain of computer vision and deep learning. And I will try to touch the basics as well as some of the very interesting aspects in this particular domain. Okay. So is it visible to all of you?
Yes,
My
sir.
screen? Okay,
Yes, sir.
great. So,
Yes, sir.
okay, good. So the title of my lecture is Deep Network Techniques for Computer Vision, and I will try to move in a not in a slow pace so that we can understand the basics of deep networks, and then we will see some of the very exciting things which are happening in the computer vision domain based on this deep network algorithms. So what is computer vision? I think the computer vision is a domain which is now maybe possibly 30 years old, or maybe more than that. But it's a domain due to the dynamic environment, the dynamic applications. Okay, it is evolving, right? It is evolving over the years, and it has become very exciting. So fundamentally, what is computer vision? So computer vision is just to try to generate vision in artificial systems. That vision is a process which happens in a natural phenomenon in the biological systems, like the human system, where we have the upper part is the human processing system. So suppose we have a real scene, right? And the real scene gets captured by our eyes and then processed by our brain, by the different sections of the brain. And then what we try to get the inference that what particular this scene means. Like, okay, there is a field and there is a cornfield and something background, blue background and something like that. So now, can we try to generate this interpretation in our artificial systems? Okay, artificial systems traditionally means the systems which are which are driven by computers. But this term is also getting evolved, right? We are evolving from the scenario where we had a camera and the camera connected to a computer to an integrated camera and the computing systems like what we have in the smart devices. And now we have different types of this. We have the robotics, we have the autonomous cars and all these things which have a very, very integrated compute. The vision and the computing system are very well integrated, right? But to keep it simple, the same thing what happens in the computer vision is in the artificial way, where we have a particular type of vision sensor. Okay, the bottom flow, if you see, it tells what computer vision is in a very simple way. So what it is actually the same scene being captured by our electronic vision system, which is normally a camera. There can be a variety of that, right? I'm again not getting into that, but then the data captured by this particular sensor is being carried forward to the processing engine. Processing engine is something, a CPU or a custom processing hardware. Okay, obviously having some software stack for the algorithm, and then also it tries to generate the same inference, okay, which a biological eye and the biological processing system can generate, right? And if you can do this very closely, which means the correctness of the computer vision application, okay, we are trying to generate systems having a vision which is very close to our biological objects, which is pretty challenging. It's not an easy task, right? If we see the literature, it will be said that still the computer vision processing in an average. Okay, I'm not telling that very very special cases of computer vision applications, but the general computer vision applications are still has a maturity which just like a so 8 months old baby, okay, what a vision a 8 months old baby has, right? In our human, if you compare it to the human, right? So still the computer vision needs to get matured so that it can be comparable with the vision of an expert human or an expert individual. And that's the process of journey what computer vision is is aiming towards. So now comes the deep learning, right? So I have skipped a lot of things and have directly jumped to deep learning because this is the present buzzword in the computer vision domain, where we try to see that means how the deep learning has accelerated the performance of computer vision, and is trying to generate a lot of applications with a very high accuracy, right? And when we say about computer vision, we actually have to name 4 persons, right? 3 persons are from the left. If we see the first 3 persons, they are Lee Kuhn, Bengio, and Geo Finton. And the last but not the least, on the right is a professor in Stanford, Professor Andrew Ng, who is a phenomenal professor, and I think who has influenced the domain of deep learning, okay, to all of us, and has okay, through his courses, through his research works. So these 4 persons are very important persons in the domain of deep learning, and that's why I started deep learning by showing their pictures, right? And it's a very, you all should go through this paper, what I have shown here, which is deep learning allows computational models that are composed of multiple processing layers to learn representations of data with multiple levels of abstraction. And this was the paper in Nature, okay, and Nature 2015, where they have reviewed the present state of the art deep learning, right? And this is this should be something which all of us should read and should know, that how the deep learning techniques, right, have evolved. So let's move on. So the deep learning, what we see at the present scenario, okay, it again just not evolved just like that. It was a long process of okay, trying to generate the neural networks at the first step, right? A sort of inference engine, neural network based inference engine, which was started in 1943. Okay, it was just like a functional, okay, just like a neuron which can do some functions, right? Similar to the logic functions, okay. Kulak and Walter Pitts, okay, tried to develop this particular notion of computing in 1943. Then the famous model of perceptron was where we tried to focus on the weights, right? Perceptron model gave us the understanding of how we can try to generate a sort of mix of the inputs based on the weight which is multiplied with the inputs, and that's a pretty fundamental model of neural network, right? It was a contribution of Rosenblatt when he showed that how the choice of weights, right, influences the outcome, right? And if you can have a good choice of weight, we can actually try to generate a very simple binary classifier. So this particular picture shows a classifier, and this line is a class boundary which separates the 2 classes, right? We have a class +1 and we have a class -1. Right? This is again a phenomenal progress in the domain of a neural network, which we just worked as a function in the previous abstractions, and now they are trying to develop the classifiers using the neural networks. Then there is something, some sort of skepticism which comes out that the perceptron, okay, Minsky and Swimmer paper in 1969 said that, okay, perceptrons are good, but perceptrons are very strong enough. They cannot separate out the functions with a nonlinear, okay? And then the concept of activation function came, right? Which we know presently that activation function are doing a lot, and they are trying to do a good. They have a great contribution in the taking the perceptron to the nonlinear space of the algorithms. So then the multilayer perceptrons and backpropagation and all flurry came into existence from okay, from 1990s, right? There was a flurry of activity, and ultimately, our key, what I can say, the most important component evolved, which is LeCun at a convolution neural network, right, in 1989, which actually just did a wonder in terms of how we can extract the features from our data, right, based on the convolution filters. I will give some explanations of this in the latter part of my lecture. But then it also progressed. Not only the convolution neural network, now we have a flurry of networks, right? And the again important step came in this particular network, which was which is a recurrent neural network, and the LSTM. Okay, so LSTM means a memory which is there with your recurrent neural network, and this type of networks were very important to understand the sequences, okay, the correlation which exists between a previous input and the next input, the output of the output generated from the previous input, right? How it influences the next input in the network, next outcome in the network. Okay, so these were the different types. This was again a very important contribution in the neural network domain or deep network domain, where we can try to analyze the data which is expressed in the sequence form, and natural language processing, application in natural language processing, application in the time series type of data. Okay, those type of applications were being considered in the domain of RNN and LSTM. Now let's come back to the fundamentals of deep learning. To the organizers, as my lecture will go on around 1 hour plus, maybe 1 hour 20 to 30 minutes, what I will try to do, I will try to give some pause in between in my lecture. I will stop, and then I will go back to the participants to put their questions, so that it can be interactive, and also I can understand whether my lecture is fine with all of you. Okay, so let me continue. I will give a pause, and I will ask for questions after some time. So now I come to the concept of deep learning, which is the underlying concept of the underlying story of my entire today's presentation. Okay, so what is the deep learning? So deep learning is a sort of inbuilt automatic multi-stage feature learning process. This has been well emphasized, right? Your traditional machine learning, which existed before deep learning, okay, right? We existed in terms of classifiers like the Bayesian classifiers, like support vector machine classifiers or tree-based classifiers. The fundamental difference between those type of machine learning techniques and the deep learning techniques is that the machine learning techniques has two-stage process. Stage one, it tries to build the feature space. Means it tries to capture the features, it tries to find which features are important, right? And the important features should build my feature space. So there are several techniques to find out the important features, okay, like feature selection techniques, or there are some techniques to understand the sort of transformation space in the transformation in the feature space, like what PCA does. Okay, so we can also do a transformation in the feature space to make the feature space better representative. So those are called the part of the feature engineering, which happens in the first part of the machine of the class of the traditional machine learning process. And the second phase is that, hey, can I build a classifier, or can I just try to generate a class boundary, or can I try to generate a clustering sort of algorithm where I try to generate a distance function, and the distance function will try to separate the data points. So these are the basic way of operation of the traditional machine learning models. The two-step process. One process is the feature extraction and feature space creation, and the second step is either you are trying to classify or cluster the data points in the feature space. So having said so, the supply or the feature extraction is a process which is done by the machine learning or the data analytics person in his or her own way. And the problem in that is that if a person doesn't have a very good understanding of the domain, because the feature comes from the domain knowledge, right? If I tell you that, okay, you try to classify a tumor or a tumor or a lesion in a lung radiology image, okay, then I can't tell you that what should be your lookout, what should be the features you will looking for, right? You have to sit with a radiologist, right, or an oncologist, okay, who has an expert domain knowledge and tells that, hey, if you look into the boundary, you will find some difference in the boundary of a tumor, compared to a normal lesion. If you look into the inside mass, you will find some sort of texture which is there in the tumor and which is not there in a normal lesion. So this represents the feature of the object, and that comes from the domain expert. So the problem is that many of the times the domain expert might not be available for you, right? Or might be the domain knowledge is not being properly consumed, and so you have done the machine learning first step of machine learning, the feature extraction was not done properly, either due to understanding or due to the complexity of the problem domain itself. Okay, so this is the issue. What happens in the case of this traditional machine learning. Okay, now the process is eased up, right, in the case of deep learning, and that is the process which is the automatic feature extraction or automatic feature learning process, right? But as I know, there is no free lunch, right? If you tell me that hey, the automatic feature learning process has been done in the deep learning, the cost is that you have to supply the enough data so that the entire domain is well captured. Okay, if you give a partial information of the domain by giving you some set of data or some sample images, then the feature learning process will be incomplete and the domain knowledge will not be complete. And that is one of the major issues in deep learning, that when you tell that I'm trying to apply deep learning, right, the first question will arise, do we have enough amount of data, right? Though having said so, though there are a technique by which we can still generate the data, okay, using some sort of sampling techniques, but that I'm again not coming. I'm just trying to say that there is nothing that thumb rule that I will go for deep learning or I will go for machine learning, right? Depending on traditional machine learning, because deep learning is also a machine learning, right? Don't take it in a wrong way that I'm telling machine learning and deep learning are different things. But all of the class, that means all of this machine learning and deep learning are actually the subset of AI, and then machine learning is there. Okay, a form of extended machine learning is deep learning, where we try to use a different way to employ the networks using the deep network architectures. Okay, so that's all. So let's look into what's the second part of this. The second part of this is the multiple layered architecture. Okay, and that's why it's called deep learning. It's a network, or it's the layers are very deeply constructed. So there are multiple layers instead of a traditional neural network, which can have maybe 10 hidden layers or 20 hidden layers, right? A traditional deep network can have very high number of layers, okay, and a large number of neurons, okay. So now what is this feature build-up process? So you see that if you see this diagram and what I've shown, right? At first, it tries to capture the low-level features, okay? So this is the feature build-up process. Suppose I tell you that, hey, you need to learn this particular book, okay? So how you start? That you need to summarize. You need to summarize this particular book and you need to tell me that whether it is a novel, right, or whether it is a scientific fiction. So how do you start? Right? You try to go through the lines in the pages, then pages compose chapters, and then go through the chapters, right, and then the entire book. So which means that you are trying to achieve the summary of the book from a bottom-up approach, right? So you first learn the important lines in the chapter in a page, and then the entire chapter you try to understand, and then you try to understand multiple chapters, and then you try to say that, okay, when you summarize, you don't summarize from the pages what is there in each chapter, right? You try to summarize the chapters, right, and then you try to keep the summary, and then you try to classify that in terms of whether the book is a novel or the book is a scientific fiction. So this actually happens in our biological brain processing also, okay? So we first try to capture the low-level features. For example, if we try to see this particular image, which is an indoor image of a house, first you can just try to capture the derivative, right? You try to do a derivative, right? Try to find that where the intensity varies abruptly, right? And then from that you can go to the edge features, and from the edges you can go to the textures, right? And from the textures you can generate the objects, and from the objects you can push that to the classifier and try to tell that, hey, these objects are indoor objects and these objects are outdoor objects, okay? And then you try to tell that, hey, this is this is what is how we can classify this particular image, okay? So this is the feature build-up process, right? So from the low-level features, we go to the mid-level features and the high-level features, and then ultimately we have something called flattened network, which works as a classifier. So now how these features are being extracted in each of these stages. The features are extracted by the convolution filters, right, which works on the patches of the images, okay, and try to generate a maximum output or a minimum output. That will tell you that whether in the particular spatial region a particular feature is maximized or minimized, right? And then you can understand the first level of feature distribution, which is called the feature space. And then on the first level feature space, you apply the second layer of kernels, which will try to, like the derivative values. On the derivative values, you apply a threshold kernel. And the threshold kernel will tell that, hey, these are edges, right? So this goes on and on, right? And these are all done by the convolution kernels. So to understand what is a convolution kernel, let's try to go with this discussion, okay? So if you see this, right? So this is an image information, okay? You can just try to consider that each of these dots are nothing but your pixels of an image. And instead of running that is on the entire image pixels, which is a traditional neural network. If you push this to a traditional neural network, right, all this will work as an input at the input stage. But vis-a-vis, when you do a convolution neural network, you try to you try to decompose this particular image into patches. And what you generate an outcome from a patch region, which is shown here, okay? So you try to generate the kernel outcome from a patch on which the kernel works, and then you generate its outcome as one particular outcome of the patch, and then the kernel moves over the entire image and tries to generate this outcomes. Normally, the convolution outcome is of larger dimension, is of smaller dimension than that of the actual image. But you can still do that by doing some sort of padding where you can still keep the dimensions same. But again, I'm not getting into that, right? Let's try to go into the more understanding part instead of how we try to set the experiment, okay? So this is what is a convolution outcome, right? Now these are spatial filters. Okay, as we know, this works on the image. Image is a spatial information. Image is a function of xy, fxy. So it means that it is a spatial distribution of intensity values. And these intensity values, as we see here, these intensity values are fragmented into patches. And on this patch, the convolution kernel operates and tries to generate a particular value. Now, there are several layers, there are several outcomes, okay, of convolution. Why? Because this particular convolution outcome is for a particular type of kernel, okay, which is operated on the patches. Now, I can have multiple convolution kernels operating, and each will generate their plane. And that's the outcome what we get in any one convolution layer. So any one convolution layer will have multiple convolution filters. Each filter will have a particular dimension, and that dimension of the filter will actually depend on that will define the patch size. If the dimension of the filter is 9 cross 9, okay, fine. In this particular case, it's a 9 cross 9. It's a 3 cross 3 filter. Okay, 3 cross 3 kernel size. So the 3 cross 3 kernel size means that the kernel will have 9 weights, right? And each of the weights will combine with the corresponding patch inputs and will generate an outcome. And then the kernel will move all over the image and generate multiple outcomes, which will be stored as the outcome of the convolution function or convolution kernel 1. Similarly, I can have n convolution kernels operated on the image, and they will generate n convolution outcomes. And these convolution outcomes will be the actually outcome of a particular layer in your deep network. And then what happens is called an activation or ReLU. So activation or ReLU, as we know, that this is a sort of function which is a switching function. Based on the input what we supply, right, either the outcome will be high or the outcome will be low. So what happens is that after we do the activation function here, the outcomes which are really low, they will not switch. They will not generate a considerable outcome in the activation layer. But the outcomes which are pretty high which means that the feature, the convolution feature, the kernel feature is maximized in a particular spatial region, right? And that will be well captured through this activation function. And then the activation functions have high and low, so we can do a max pooling, which means that within a particular window, you take the max value. So which means that it subsamples the particular space, right? And it tries to give you a very condensed feature representation, so that on this, again, another convolution kernel can work. And this way it goes on, and ultimately this, or in the last layer, all these convolution outcomes are being generated as a single vector and are pushed into the classifier. Okay, so the classifier can classify the vector, which is also called the flattened layer, generated by multiple convolution kernels working on multiple layers. Okay. Now to understand this, this is a part of this is a small animation which we can see that. Okay, I think all of you know. So now I come back to the participants. Okay, just to put a question. So who can answer me that what this convolution kernel represents? What the filter represents? This filter that is -4 at the center and 0 at the 4 corners and 1 at the left, right, and top, bottom. Who can answer this question? What this kernel represents? So I just want to make the thing interactive, okay? So that all of us are well connected. So any answer from the participants? What this is a simple example of a convolution kernel. Now, what this convolution kernel will generate? Who can answer? Any answer from the participants? I have shown the results, so I think you can now guess.
There are some questions already there in the message.
Yeah, I will come to that, but just what I can say, just an answer to okay, okay. If anyone can answer this.
Subro, this is your area of research. You may try to answer.
Yeah, I think yeah. So this many of you will answer. No answers. Okay. Okay. So if you look into the kernel, right? I will again go back. Okay.
Laplacian operator. Is it Laplacian operator, sir?
Yeah, it's a simple operator. Okay, it's a simple operator. If we go back and see, it's a simple operator which actually tells what it tells. It tells that hey, you have a center -4, so the center value is subtracted, right? It's subtracted from the center value. If you see this, I think it's visible to all of you, right? So the center value is subtracted, okay, from its top, left, bottom, right, okay? So it means that, okay, if the center value, if the center pixel is pretty different from the left, right, and top and bottom, right, the value will be considerably high. The kernel will generate a very high value in that particular spatial region. Okay, but the center pixel is very different, because you see if these pixels are say 100, 101, 102, 103, right, and if this is also 100, then you see that 400 minus 400, 3 or 4 is a very small value. But suppose these are 50. Okay, the top, the left, the left, right, top, bottom are 50. Right, and this may be 100. Okay, if this is the value, then you see that the 4 into 100 is 400, and 50, 50, 50, okay, is 200. So the difference, as I've given -4, means means it is subtracted from the from the summation of the left, right, top, and bottom pixels, and the subtraction and the subtraction value is quite high. So if it is quite high and above a threshold, then this particular pixel will be defined as an H pixel, because the property of an H pixel is that it has a very high derivative value. Okay, so its difference from its neighbor pixels are pretty high, and that what is, right? This is a simple H kernel, right? So if you operate this H kernel over this entire image, right, it will generate high values. Okay, right, in the regions where there are edges. Okay, so this was my answer. Now let's go back to some of the discussions or questions. Okay, where I can get the questions. Any answer? Any? Let me see the questions where they are. What are the questions? Can anyone help me to find out?
Yes, sir. The first one is from Alim Say. And he says, is it necessary to have trained classifier always?
Oh, this is okay. Now I got a chat window. Okay. See, classification is a supervised problem. Okay, supervised okay, algorithm. So if you are training classifier, you require training, right? But if you are training clustering, it's an unsupervised problem. Okay. Now there is something called semi-supervised also. So semi-supervised means that, okay, you have a very small amount of training data, right? And you need to classify a large amount of data. Okay, so your domain representation is pretty weak. Okay, because if you have a small amount of training data, it means that your domain representation is pretty weak, right? So that's called a weak classifier. So what you do, you actually push your push your data which is available. Okay, you push your data which is available to that weak classifier. Now the weak classifier will give erroneous results for a majority of data, but still some data it will separate very large values. So the separations which are good, those you can again take as label data and you can build the training set, right? And then you retrain the classifier using the enhanced training set, right? And this enhanced training set will make the classifier a little bit better. And then you try to again work with the unlabeled data, again push the unlabeled data, and again try this cycle. By doing this cycle, what you are actually doing, you are actually generating from a weak classifier to a strong classifier, and also it is helping you to label the data. This is very often done in a new domain, right? In a new domain where the data is not very available, and if the label data is not very available, you cannot actually build your classifier. So you start with a weak classifier with a small amount of label data, and if you are successful enough in this particular semi-supervised process, right, you can do it. The other distraction here is that, okay, you can start with a very well classified model, but it doesn't work in the many real scenarios, because the real scenarios have a lot of differences which was not being induced in the training data. Now, who can answer this question? This is like a machine learning general knowledge question, okay? Not a common GK question, but this is a machine learning GK question, okay? So who can answer this question that, hey, I have a classifier, I have a trained classifier model, but the model is not experienced to variations which happens in the real scenario. So what to do now? Who can answer this question? Okay, I don't have any. So if it was a live webinar, I could have offered some. What I can say, some bounties to the participants who can answer me well. All right, but here I don't have any way to do that. But I can appreciate who will answer this question. So I have defined one classifier, which is a weak classifier, to progression to strong classifier, which is called a semi-supervised learning. And there is also another type of learning process.
Excuse me, sir.
Sure.
I am Shubhra, sir, and I am willing to approach this question actually. And
yes, please go ahead.
If we can use, it is always necessary to use trained model.
Mm-hmm.
Suppose my problem. Suppose I am using a model which has been trained on image segmentation or image classification problems. Now my domain is not image, so I am going to suppose I want to use that in audio classification or something else. So I believe in such cases where the data is totally different from the model, from the training set, so there I can build my own model and start training that model from the ground, because my data is totally different. So I am.
Yeah, Shubhro, you are right. I am not going into that. That means I am telling that you can always build your scratch model if you have enough data. So I have give two options. So as you have said that there are, so there can be two way outs here. So the first way out is, first problem is that, as you said, that you have a data, you have trained a model in a particular domain with enough amount of data. Now you switch the domain.
Yes.
right? And there you might not have a large amount of data. What you can do? This is also a good question. I will come to that. But my question was a little bit different. That I have trained a model, right, in a very good training data. But now what happens is when I go into the real time, right, I see there are a lot of different scenarios which can also offer, which is not there in my training data. How I can handle? So this technique, this technique is called reinforcement learning. Okay, so reinforcement learning is a learning. Yeah, perfect, Kajal. Yeah, that means I don't know whether you're a professor or you're a student, but you are very right, Kajal. That this is called reinforcement learning, where we have a baseline model, right? And this baseline model, when it opens up in the dynamic environment, you cannot do. So what I will say, okay, let me give an example. Say all of us know how we can walk, right? But now I push you in a region, okay, where there is water and mud, and you have very less amount of light, okay? So though you know walking, right, can you walk in that region without making your foot get hurted? It's a difficult problem, right? So that's reinforcement learning. So what do, right, in that particular scenario, you first place your foot, right, and try to understand whether this foot is stable or this is slippery. If it is slippery, if your step is slippery, you just take your foot out, and you try to see that what is the next step where you can place your foot. So when you take it out, it means that you are getting a sort of penalty, not a reward. But once you place a foot in a particular region which is very stable, right, you now take that particular direction because that is giving you a reward. So this is called a very simple example of reinforcement learning, which is called walking in baby steps. It's another dimension of this problem. Now the problem what Shubhra you have said, this can be taken care of the transfer learning problem. Okay, so transfer learning problem is a problem where you try to build your model using a very good domain information, and then you push it to another domain where the domain information is not so strong, and you don't know whether your model will work or not. It is it is similarly it's very similar. That means if I tell you to read a novel, a very classical novel, it's a Booker's Award novel, right, which may be a very complicated that means it may be a little bit tough for many of us, right? Okay, but to achieve that, I will tell you that, hey, can you just go with a very simple book, simple book written by a very in a simple author. Just try to know that how the literature build up works up, right, and then go to the higher level of this book. Okay, so this is the process of transfer learning. First you try to learn the best features, right, and then concentrate on the features which are very specific to your domain, right, and then you can migrate from domain 1 to domain 2. So these are certain techniques which are there when you try to change it. As the fundamental question was that, can we actually adapt the training in the classifier domain? Yeah, we can do, and there are different varieties are there, which varieties of techniques are possible. But when you tell classifier, that means you require at least some sort of training model to start with. Okay, so am I clear to the first question? And let me see the next questions what are there. Okay, so any other question? So are you satisfied with my answer, Shubhro?
Yes, sir. Of course.
Okay, good.
It's more than
There is another question there. How to choose the convolution mask for filtering?
This is a very good question. This is a very good question. So this is based on the error. Okay, so the problem in the deep network is that, okay, deep network is an engine which is a black box, right? Because there are so many layers, right? You cannot actually get into each layer and try to fine tune that. It's not possible for you. So what you do here is that, right, you try to see the end layer. So you start with a particular simple kernel type of architecture, and then you try to, so suppose you use a baseline VGGNet, right, and try to do the training. I'm just saying VGGNet, which is a very conventional, object recognition, okay, process. So what do? We try to use a baseline VGGNet and try to use my particular set of data, right? And to the training process, it will try to reduce the error, right? And when it tries to reduce the error, what it's doing is actually adjusting the weights of the kernels, right? It is going first at the last kernel, and then trying to see the influence of the previous kernel to the last kernel. So this is a gradient function, right? It's called a backpropagational gradient operation. So the error is a function of your weights. As you haven't chosen the kernel weights properly, right, your outcome is not good. So now you try to find the derivative of the error in terms of your weights. And the weights are in several layers, right? Which weights I'm talking about? So the first weight will be the last filter, but that weight is again dependent on the previous layer filter, and that depends on the previous layer filter. So this goes on, and so ultimately in a process, okay, all the weights gets adjusted, right? And this is how good you develop the error function and how good you do the training. So in each training cycle, you update the weight parameters, okay, of your network. And in the slow but steady process, there is something called that is, you have to reach the minima of your error. It's called the gradient descent. So wherever you are, you have to descend from the maxima to the minima, and that minima will give you the error minimization, and that can be done by adjustments of weights. And this is done by these networks to the training process by the optimizing function. You will see there are optimizer functions which are applied, like Adam optimizers. Okay, there are some very good optimizers are there, or simple gradient descent optimizers. So these optimizers will actually modulate your weight in each of your training iterations, and you will stop when you have received a particular error between a threshold based on your training data. This is called a training error. When the training error is within a particular limit, okay, you can stop this training. Okay, it's not a deep learning lecture session. That's why I'm not getting into the details of the how it is done. But this is just a tutorial. So I'm just giving you the hint of the processes which can be done. But if it's a machine learning or a deep learning lecture class, I normally take for some of the for some of the institutes abroad, okay, where we try to discuss it in this form, right? So this is all I feel the answer. Okay, are you satisfied the answer?
Yes. Can I tell it?
Yeah, this is the last question I will take before I move forward. Okay, yeah, please go ahead.
Just little thing, sir. Sir, the depth of the network, is it always the case that the accuracy of the network always depend on the depth of the network? Is it always the case?
This is a very good question again. Okay, this is a very good question. So how the depth of the network? See, depth of the network. Okay, so this is again a fundamental understanding. I normally discuss this in my neural network class, and that is how we understand the depth. Okay, so let's try to take an example. Okay, suppose I have blood parameters as data, right? I have the blood parameters like okay, my blood sugar parameters, my blood cholesterol parameters, my blood urea parameters. 3 parameters. Okay. So 3 parameters tells me that whether I am diabetic, whether I have some problems in my heart, or whether I have some problems in my kidney. Okay. So these are 3 convolution functions, okay, on the same data, right? One convolution function will try to explore my data set and will try to find that whether I have maximization in diabetic or minimization in diabetic. Another convolution function will work. It will try to find out whether I am maximized in the heart or minimized in the heart. Another convolution, because for cholesterol, it's not that the cholesterol is very independent of the heart condition, is very independent of diabetic or my blood urea conditions, right? There is some weight for this, but the weights of cholesterol are higher, okay, for my heart condition than the weights of the diabetic conditions and urea conditions. Similarly, for the diabetic condition, it's not that they will not take away take the value of cholesterol or blood urea. They will take, but their weights are less, right? And the weights for cholesterol, the weights for the diabetic is higher. So there are three convolution functions, okay, which operates to extract whether diabetic high, diabetic low, whether kidney high, kidney low, or whether heart high, heart low. Okay, this forms one layer. Now, what can be the second layer? Second layer can itself be an inference engine. Means whether I have a multi-organ problem, or I have whether my problem is very high, whether my problem is very mid, and whether my problem is very negligible or not problem at all. So I can tell that if you have more than one organ problem, then it's high. If you have one single organ problem, then it's mid. If in all the organs you have no, then it's no problem. So this is a classifier. Okay. Now suppose my end goal is not disease. My end goal is stay in the hospital. Hospitalization day. That is how much duration I have to stay in hospital. Then the duration of stay in hospital will occur based on your disease condition. So I have to put one more layer, okay, which will work on the disease condition and will generate the hospitalization class. So now do you understand what's the concept of layer? So it means that how long you want to stretch the feature space and you want to come to the inference, where you want to draw the inference. Based on that, you have to go on adding the layers. Okay, am I clear? If you want to decide based on the ages, you can just put classifier after ages. If you want that no, ages will not give me the information, you want to go to the texture, then you have to put the classifier after the texture. Okay, so the number of layers means okay, how you are building the feature space from high to low level. That is from low to high level. Fine. Are you satisfied with my answer, Shubhro? Okay. So Shubhro, are you there?
There are some network problems, I think.
Okay, fine. So I am going back to my presentation. Okay. Okay, is it visible to all of you now? My screen? Okay.
Yes, sir. Yes, sir. Yes, sir. Please carry.
So this is the way. So just to tell the animation that if you again go back, so how the convolution works. So this is the way the convolution works. It just moves over the entire, the patch-wise, okay, over the entire image, right? And what you generate the convolution outcome, because this was just an edge detection filter, okay. Now let's try to see that how we can learn an image, okay? So to learn an image, basically for the patterns which are there in the images, okay? So if I am try to understand a particular whether this image is of a bird, what I need to understand, I need to understand whether this image has a beak, whether this image has a tail wing, and whether this image has a legs with some sort of paws. Okay, so I have to generate filters which will try to detect each of these patterns in my image. And if all the filters says yes, 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 I have a beak, yes, I have an eye, yes, I have a tail wing, yes, right, I have a leg with having some claws, yes, then I am without looking into the picture, I am telling it's a bird. And that's the way the classifier works. Okay, so the work of the classifier becomes very easy because the deep neural convolution layers extracts these features and pushes it to the classifier very diligently, and that actually makes very complex recognition a simple process. Okay, so this is the process. So what it does, it tries to so the convolution in the spatial patches. Okay, nobody have asked this question. I thought that somebody will ask that, sir, what is the significance of spatial patches in convolution? This is a very good question I normally ask, right, in many of the discussions with my students. So the question is that, sir, why the need of the patch of the patch-wise operation of the convolution functions? Because the patterns are spatially located. See, if you want to try to find the beak, right, it will be only in one spatial region, right? You don't need to search the entire image to find the beak. So what do? You try to partition this image into some patches, right? And you try to convolve these patches with the big filter, which is something like this. Maybe this is a big filter. And big filter will tell, okay, it's a big filter, okay? B-E-A-K, big filter, okay? And big filter will tell that, hey, in this particular spatial region, I found a big filter value 1. So I registered that this particular image has a beak, right? So this is a big filter which actually generates a weight so that the big pattern gets maximized, and this is an activation function which generates a high outcome in this spatial region, and this marks the identification of big in a particular spatial region. Now the good point of convolution kernel is that suppose this particular bird shifted here or shifted here, no problem. I am running the big filter in all the patches, and in one patch I will record that this is a big filter, big is present, so I can still find that whether this is a bird or not, independent of the orientation of the bird. Now many of the classical machine learning processes, machine learning filters, machine learning algorithms which works on different types of like we have the sort of some sort of coding, some sort of neighborhood analysis, right? You can miss this type of spatial invariance. So the convolution kernel operation is done spatially so that the operation is spatially invariant. So it doesn't changes. Okay, the feature space doesn't changes if the beak instead of here is here, or wing instead of here is here. Okay, so I hope that I have made you understand that what is the importance of the spatial kernel, spatially localized kernels. Good. Okay, so this is a big detector, right? And this is a big kernel, as I said, right? Can represent a small region with fewer parameters. This is also very important. I will come to these parameters immediately in the next slide. So this is a good important issue, right? As you say that, okay, that is okay. Okay, it doesn't makes me any difficulties, right? If the beak is here or beak is here, you can still detect a beak either at the upper left or at the middle of the image. Still, you can detect the beak. Because it actually works, this big filter works over the same way in this image and this image. In this image, it traps it here. In this image, it traps it here. as the spatial window, okay, as it works on the spatial window, it can always trap a BIC in any of the spatial window in another image. Okay. So one issue is that one very important issue is that as one questioned me that sir, okay, that means how the training works. This is a very good example how the training works. Okay, so you see that you can generate a BIC detector filter here, and in the next training input image you detect a BIC detector filter here, right? And considering these two BIC detector filters, right, you can generate a homogeneous BIC detector filter which can work for both of this type of boards, because there is a little bit different of this BIC. This BIC is a little bit straight BIC, and this is a little bit curvy BIC. Okay, so little differences will be there, but still you can generate a particular filter which will accommodate this BIC as well as this BIC. For both the BICs, it will be high. And that is done by if you give lot of boards with lot of different BICs. Okay, they are labeled as board because supervised learning. They are labeled as board, and you supply them with a lot of BICs, a lot of board images having different types of BICs. So all the independent BIC detectors will be clubbed and will be generated a particular filter which will able to detect, their weights will be such that they will able to detect all the BICs, all the different types of BICs. Okay, so that's the important part of deep learning filters. Okay, so this is something like that. As I already said, that different copies of the same feature detector with different positions. So there's a replication across scale and orientation, no problem. If the scale increases, if the orientation changes, no problem, because you are replicating, you're running the same filter on the spaces, okay, on the spatial patches. Okay, so this is the scenario. So you run the filter in this patch, you run the filter in this patch, you run the filter in this patch, and try to record whether high or low, right? So this is the issue. So the BIC detector is a kernel you developed, which works on the patch of the image and generates whether the value is high or low. And that's what is CNN. You have several this type of detectors. Okay, and each detector works on the patches of the image. Okay, it just, as I shown in the animation, it moves like this, and computes the outcome on each of these convolution operations, and to know that which region has this filter value high, or rather which region has this feature value high. And then you have number of filters which are occurring in one layer. So each of the filters will generate their high-low values across the spatial distribution of the image. Okay. So this is what's a convolution. Filter 1, filter 2, ... filter n, right? These are example 6x6 image, right? How it works. Filter 1, okay, works on this part. Then it does a dot product, means 1 multiplied with 1, -1 multiplied with 0, -1 multiplied with 0, -1 multiplied with 0, and all these are multiplied individually. These are, so if you are very conversant with the neural network, where we have an xi multiplied with wi, right? So for this particular filter, these are all wi's, and the input, these are all xi's. Okay, so the outcome of this is summation. Okay, I think all of you know summation. Okay, for I equals to 0 to n, okay, wi multiplied with xi, and the same thing is done in the convolution kernel also, convolution operation also, because this wi is multiplied with this xi, this wi is multiplied with this xi, and you sum all of them and ultimately generate the outcome. Okay, so let's see what's the outcome. The outcome here is 3. Why the outcome here is 3? Because this particular filter and this particular space matches perfectly, because this particular filter says that, hey, I will have all ones in the diagonal, and this particular patch, image patch, has the same stuff. Okay, But in the other regions, the value is not so high. Okay? So this is the process. Okay? To generate the convolution outcome of this particular filter working on, and you see the values are 3, 3 in those regions where this particular pattern is there. So it has generated 3 here and generated 3 here, because in these 2 regions the pattern trapped by the filter and the pattern existing in the image exactly matches, right? Perfect. We have a perfect map of the filter and the image patch, and that's why we had a very high value. Good. Perfect. So repeat this for each filter. So this is the outcome of filter 2. Filter 2 kernel changed. See, the filter 2 kernel changed. And again, you try to see where it will be. Okay, this is again question. Can you tell where the filter value will maximize for this particular kernel? It will maximize when we have this particular pattern in my image. And let's try to find out where it is. Okay, so the pattern is here. This particular pattern and this particular pattern in the filter maps directly. And that's why this is a 3. So I know that this particular feature is present in this spatial region. Okay, this may be the big filter, and this may be your tail filter, maybe, or this may be some, okay, maybe your leaf filter, or maybe something your leg filter, whatever it is. Okay, so this is the feature map. Okay, so each filter generates a feature outcome, and that generates all the feature outcome generate the feature map. Okay, now what do we do in the color images? We have 3 channels: red, green, and blue. So you generate each filter for each of the channels. So when you use an RGB image, instead of the dimension XY, it is XY3. 3 because you have 3 layers of XY. Okay? In any kernel representation or any input representation, you have this particular representation of color images. Okay? So there are 3 layers of filters because there are 3 layers of images, right? Now let's try to compare this. This is a convolution operation, what we are doing, okay? And this is a very fundamental of ANN. In the case of convolution, we work in patches. In the case of ANN, here, this entire image will be represented as a single vector. So we have 36 elements in that image. And in the case of fully connected network, we have all this information as a single vector, x36. And let's try to find out, okay, where we gained and where we lose, okay? So I will just go into the end part, okay? So see what happens. In the case of a 6x6 image and having a kernel of 3x3, okay? So how many parameters you have? Okay, you actually need to fix 9 weights here. I think all of you agree. In terms of the weights, these are the weights. I've already said the filter coefficients are actually the weights, which are equivalent to WI of your traditional neural network. So for one filter, you only require 9 weights because the filter dimension is 3x3. In the case of a neural network, classical neural network, you require 36 weights because all these 36 inputs will require 1 weight to generate this particular outcome. Okay, right? So number of filters here, say there are n filters, so it will be 9, and each filter are 3x3, so it will be 9 cross n. Let us take there are 10 filters. Let us just take an example. So 10 filters, and each filter has 9 weights. So we have 10 into 9, 90 parameters. Now suppose we have similar 10 nodes in the next layer, okay? And we have the full 36. For each of the nodes, full 36 weights we need to generate. So we require 360 weights. Okay, so 10 into 36 is 360 weights, and 10 and 9 into 10 is 90 weights. So I've reduced the weight by 1/4. And larger the size of, this is only for a 6x6 image. We don't have a 6x6 image. We have a 200x200 image. So try to imagine for a 200x200 image, how much weight reduction you have done in the convolution neural network compared to a classical neural network. And secondly, classical neural network doesn't represent any spatial correlation. In the convolution function, as I rightly said in the previous slides, discussing the previous slide, that the spatial correlation is restored in the convolution operation, and that's the advantage of convolution operation. Okay, I will not go into much of this now. This is very straightforward. So after you do this, you can have a max pooling where you try to make a 2x2 window, and you try to take the maximum value in this window. So for this, the maximum value is 3. For this, the maximum value is 0. For this, the maximum value is 3. And for this, the maximum value is 1. So after max pooling, you can just keep these values. Why is this critical? Because these are the important values, because you are extracting features, right? You are not extracting everything. So the features which are producing high values, okay, those information is to be propagated to the next layer. Okay, so that's why the max pooling, and max pooling reduces the data size for the next layer, because as we have several layers, right, if you don't compress the data, right, you will be having a flurry of, that means you have lot of weights to work out. So this also reduces the weights in the next layers, right? So pooling is a sort of subsampling, right? And that's the way it does. Okay. So these are the advantages of this. As I said, that reducing the number of connection, shared weights on the edges, max pooling further reduces the complexity. These are the very, very good way of representing a very high dimensional data, okay, and extracting its features and trying to generate a good classification outcome. Okay. So let's actually skip all these things, and this is the whole process. Okay, convolution, max pooling, convolution, max pooling. But you can also do, as I said, you can also do the the particular switching function, okay, which is called activation function, right? Somewhere you can, okay, after convolution outcome, you can just make the convolution outcome high and low, so that the pooling operation is done easier. You can select between 3 and 0 very easily, but selecting between 3 and 2.5 is a little bit, or between 3 and 1.5 is a little bit difficult. It might be difficult. So the activation function actually makes the task very simple. Okay. So that's the way, and then it goes to the fully connected network. Okay. So this is the operation of a rectifier. This is activation function. You see what it does. Okay, activation, there are several activation functions, right? There are the activation functions like you have the sigmoid activation function, you have the tanh activation function, you have the ReLU activation function. The ReLU activation function is something max of 0 and Z, where Z is the input. So it means that if Z is negative, the outcome will be 0, because max of 0 and Z. So if Z is negative, 0 is maximum. So 0 will be the outcome. But if Z is positive, it will remain the value of Z. And that's what is a ReLU, right? So you see this is a ReLU function. So it's a ReLU is also a ramp function in the positive half. So whatever is your input in the positive half, okay, the outcome will be same. If you have input in the negative half, your outcome will be 0. So you see what happens in the ReLU is that all the values which are negative are being pushed to 0, so that they don't confuse the next level, right? And that's the function of ReLU. Okay. And this is a stacking, right? And this convolution operation, the ReLU operation, max pooling operation works on each of these outcomes. each of the convolution. So this is a convolution outcome. 3 convolution filters are being applied, and 3 outcomes. In each of the outcomes, we operate a ReLU, right? And then the outcome becomes this, right? And then you have the flattening. Flattening means you have the convolution outcomes. So you first take this, fill this, then you take this outcome, and then you make the next part of the vector. So flattening layer is a single vector, which is now a common neural network. Try to understand. Now after you flattening, this is your common neural network approach, right? But we're not pushing the common neural network approach at the first step, because at the first step, these particular feature values are being extracted based on the spatial information, right? And that helps you to the classifier. If you don't do this filtering and you just straight away put this into the layer, the spatial correlation will not be captured. So these features captures the spatial correlation, and then you flatten it, and then you can put the classifier. Okay, so this is a fully corrected network, which can be a multi-layer MLP again. Okay, so this is putting all together, right? This is the way how you do. So this is a particular data set, which is a very common data set called MNIST. It's a handwritten images. So the input maybe 28 plus 28 plus 1 means 28 plus 28 is the X and Y dimensions, and 1 because this is a binary image. If it was a color image, it would have been 3. Now this is a little bit reduced and converted to 24 plus 24 image. Okay, and N1 is the number of convolution layers which are working in this particular number of convolution filters which are working in this particular layer. So there are N1 number of convolution filters. The filter outcomes are being generated. These are the filters, right? These are the filters. The max pooling reduces the dimension by half. So 24 plus 24 becomes 12 plus 12. And you operate the same number of filters again. And this process goes on and goes on, right? And then it is become flattened, and then this is a classification. These are classification levels 0 to 9 because there are 9 digits. So the classifier will map each input, convert it to a flattened layer vector, and then the vector will map to any one of the classes, and your classifier is done, right? And that's the way you need to understand a convolution neural network. Okay. Now I will go back. Okay. So yeah. So I think that I'm almost end of my lecture. Right. I will. There can be some more applications, but I think due to the limitations of time, I will not get into details. I have a separate type of lecture series which works on the. I don't want to confuse you with something a little bit different. I have a lecture series which is on the video analytics, where I discuss about the multiple type of convolution, 3D CNN, and the different types of multiple streams in the temporal and spatial streams, and how we do a fusion on that. So these are the works what we are doing at latest in the domain of of the deep networks, apart from medical imaging and all these things. There are a lot of applications can be discussed, but I think I don't want to stretch a particular online presentation much. It's ideal that online presentation should be within 1 hour, but I have already stretched to 1 hour 30 minutes, and maybe some more questions I will discuss in the latter. But but anything on deep network and computer vision, I will be very, very happy to interact with all of you. Just to end this, we have a fantastic research facility at the School of Information Technology, A.K. Chaudhary School of Information Technology, University of Calcutta. I think some of the participants know what we do here. We do multiple activities in this particular domain, and it's not only me. There are other researchers also who are giving very, very, very good effort in this particular activities. So we have a very strong group in computer vision. We work in computer-aided disease detection and diagnosis. We work in video analytics. Recently, we had a a very good pattern recognition paper in video analytics with ISI, with collaboration from a senior professor in ISI. Okay, but we are working more on this. We have a collaboration with HCL. We started this activity, and some of the interns are working very good in this particular domain. We also have an Indicon paper this year. Just yesterday, they accepted our they sent us the mail of the acceptance of a very new kind of activity in this video analytics. We have recently got a project from DRDO in collaboration with IIT Hyderabad. It's a very special project which actually defines on the computer vision and its custom deep learning implementation. I will not get into much details on this, as the project is funded by DRDO. We can't disclose much of that, but it's a very exciting research which is coming up in my lab, and a lot of students are working in this domain. We have a fantastic activity in the time series analysis, which is basically renewable energy. We are working on prediction of forecasting of power generation, and that's a good activity has been done. We have PhD students. We have researchers who are also very actively involved in these activities. We have a group of text analytics where also we have PhD students, and we also have other researchers who are doing very good work in this domain. We have a core domain of IoT and Edge analytics, which are funded by different funding agencies. We have recently submitted a proposal with the joint work of SIDAC, Samir, and SMIT with our group. We have a collaboration with IoT based activity with University of Florida. TCSL funded one of our research activities here. We are expanding this activity also in different ways. Okay, cybersecurity is one of, again, the core domain. We are trying to explore how the pattern recognition and machine learning can help the cybersecurity analysis, cryptanalysis, and we have just finished a particular funded project from DRDO, and we also got a funded project of Intel India last year, and we finished that project where we tried to explore the different types of ways we can do the AI as well as bio-inspired algorithms for the hardware security in cloud platforms. We have a very good, exciting group of quantum research, quantum computing research, and we're developing a group of quantum machine learning, which is also coming up very good way. And we have also established a particular research project, as well as we have established our students have established one of our startups. Okay, first startup in Eastern India on this quantum activities called QRD Labs Kolkata. Okay, so this is all, and this is a very exciting domain of deep learning, machine learning, which I got into from the start of 2014, when I was given the responsibility being the principal investigator of the Center of Excellence under the COE program of TechCube 2, right? And that's my journey of machine learning, and then transformed to deep learning. And now I'm heavily working in this. Some other more informations. We have recently written a book on deep learning. Okay, it's not only me; it's to other very good researchers in this domain, Dr. Saptarshi and Dr. Amit Das, with Pabitro from IIT Kharagpur. He is also a phenomenal researcher in this particular domain of machine learning, pattern recognition. So we four combined, and we published a book under the Pearson on the deep learning, and it's available on the Amazon. You can all go through that book. I will be delivering a total lecture course on machine learning under the IEEE Computer Society online tutoring program. It will come up very soon. I am also connected with Springer Diversity program, where I'm mentoring some of these online courses of Springer and machine learning, Python, deep learning, and some of the core components of that course. So there are some exciting things which are coming up in the due course of time. Stay connected and try to know that what's the way we can discuss, and we can have forums and platforms of deep learning, machine learning in the next in the near future. So thank you all, and thanks again to the department and to the university for giving me the opportunity to present this lecture. And now I'm open to the questions once again.
Thank you. Thank you, sir, on behalf of the entire organizing committee for such lucid and informative talk. We can take some questions from the audience now. You may please raise your hand by pressing the button or unmute yourself and place your question. Thank you.
Hello.
Okay, so Alim Sheikh, I have seen a question. If I can answer this, what are the positive and negative values? Very good question. So this is the way I will define a filter, right? So positive values are those, okay, which will try to combine with the input. See, values are here are weights, okay? The kernel values are weights, okay? So positive values where I keep the positive values, it means that the weight multiplied by the input will be maximized. If I keep negative value, as ultimately we are doing a summation, if we choose a fundamental neural network, okay, it's a wi dot xi summed over I. So where I put negative weights, which means that those particular inputs will have a reducing effect. So which means that I have a maximization region and I have a minimization region. So maximize. So assuming the pattern which I'm trying to explore in my image, right? I will keep the high values, right, in those particular neighboring cells. Okay, and the neighboring values will be either 0 or -1. Many other times we keep it 0, but -1 actually gives a good competition between the strong points of the feature and the weak points in the feature space. Okay. Okay.
Anyone else?
Sir, if we have a picture or pattern, it will have to come a variation, 15-degree or 20-degree variation, then how can we match that pattern with our image?
Can you repeat that? Means you are telling that a pattern has a variation, right?
Yeah. Sir,
Yes, sir. His question is already there on the message panel.
Okay, this is
Burman.
Okay. What happened in the case of match if the image pattern have 180-degree variation? So no problem. Okay, if there is a 180-degree variation, right? 180 variation means you are just having a left to right or right to left or top to bottom and bottom to top, right? Okay, so the way you need to, so what will happen? You know, the ultimately the kernel weights, what I have given static here, right? This kernel weights will be adjusted, right? And sometimes they also actually work on a little bit of this kernel, which can also have a sort of rotation. That kernel can rotate also and can try to get the spatial maximization. So it will try to generate a sort of spatial maximization by rotation function also. But those are a little bit applied in some very special cases. But the thing is that the way the kernel will generate the weights by the training process, they will always try to maximize the weights, right? The patterns which are generating the score for your classifier labels, okay, are well matched, right? So ultimately will generate to the weights which will try to extract the patterns in the way, because if you have a very good error function, so that's the other fundamental part of this particular neural network is that how you build up your error function, whether your error function can actually explore the feature space, the errors which are generated by the non-accurate feature extractions to your kernels.
Sir, one more thing. How can we generally extract a kernel from a pattern? Say we have to find out a pattern, then how can we get that specific kernel from that pattern?
So the question again, you try to understand, in the case of CNN, right, you are not extracting the feature in the handcrafted way. You are not designing anything for extracting the features. Is the network what it is doing. So how it does? It does by reducing the error, okay? That means your network will map it to a label X, and your training data is level Y. So there is an error. So the network will try to again readjust its weights at the various levels, and it will go through an optimization of the error. And in this process, it may take a bit of long time depending on the complexity, okay? But ultimately it will try to exactly catch that particular, generate that particular kernel weights, which will extract this particular feature out of your data. So it is not that you are knowing the feature and you are generating the kernel. Don't do that in the CNN. Then it becomes a handcrafted type of feature extraction. Though people are doing now, they're doing a handcrafted, just like an help to the CNN, further CNN. But if you take a very, very, very fundamental CNN, it doesn't work on handcrafted features. Okay, so the error function and the optimizer will slowly and tune. And it is so different that the way you try to tune the weights and the way the optimizer and the error function will tune the weights may be different. Okay, but still it works. And that's the case where the next level of discussion comes up in the neural network. As deep networks are black box, people are trying to explore that whether explainability of the black box can be generated. And that's a new direction of this type of network called explainable deep networks. Okay, where we try to see that what exactly answer you are telling, that how the kernels have been formed and how the feature biasnesses has been generated. Whether the feature biasness, what the kernel has generated, and the feature biasness of the domain are perfectly matched. If they are not matched, then you need to again redesign your network. So there are something you can do. That means you can give a sort of choice of number of convolution kernels you do, the size of the kernels you do. These are the choices you do, but the weights are fixed up by the training process. Okay.
Okay, thank you, sir. Now it's clear.
Before proceeding with further questions, I have a small announcement. The feedback form link is already available in the chat box. I would request all the participants to please submit that as soon as possible. Now we have a few more questions available with us. Mr. MD Aziz has asked that he has created a filter by considering the total value sum, the filter equal to 0, and works fine for him. But he have a question: is there any criteria to build a filter?
Okay. See, again, I'm telling that the criteria to build a filter, okay, is not, we are not designing any filter actually. If we are designing the filter, we are actually, see, there are some standard networks, okay? So the standard networks, if you look into the networks, they have the different types of filters, okay, which are some are based on the spatial informations and on different scales of spatial informations, okay? So the baseline network, like you use a VGGNet for object recognition and classification, or you use a UNet, okay, for those. So those networks have a standard filter architecture, right? It tells that, okay, these are the number of filters, and these are the way the pooling layers will work. These are the way the activation layers will work. You can always do a modulation on the architecture. The next thing comes the filter weights, okay? So filter weights are completely adjusted by your training process, okay, and your optimization function. If you are using an Adam optimizer, you can come to some level of accuracy. If you are using gradient descent, you can come to some level of accuracy. There are other optimizers also. So that is the process how we try to generate the filter. So there are some baseline. You can okay. If you are telling that, oh, I will try to generate a new network, what does it mean? It doesn't mean that you are generating the network having weights. You are generating the network architecture. The network architecture depends on how many convolution kernels you will use in one layer, or how many layers you will use, or where you will use the pooling, where you will use the activation. These considerations are depending on how you are trying to generate the feature space. But what exact feature values you generate, that depends on the weights. And once you create the feature space description, then what are the feature space build up? Now the feature values according to the feature space will be generated by the training. But sometimes you may fail. Sometimes you may see that, okay, the feature space is not generating good values. Then what you have to understand, that the feature build-up is not good. Then you have to either increase some more layers so that you have a much deeper feature space extraction, okay? Or you can try to introduce, okay, more number of filters, which will try to take more features, more accesses in the feature space. See, there are two things in the feature space. One is the axis, it's in hyperspace, right? So the axis depends on the number of independent features, right? And the length of the network tells that how the feature transformation takes place from space level 1 to level 2, level 2 to level 3, level 2 to level 4. So these considerations depends on your architecture. But the weights, once you settle this feature space, then the weights comes into play, which depends on your training data and your optimization function, how you optimize the error. Okay, so these are the tools and ammunitions by which you need to generate the network. So am I clear?
Mr. Ajit has asked this.
Yeah.
Yes, sir.
Yes, thank you, sir. Now,
Thanks.
there is one more question from Praveen.
Yes,
Good
sir.
evening, sir. How to decide the activation function?
Oh, that's a very good question. So, okay, so activation function has a normally, if we see the sigmoid and the tan H activation function, I had a very beautiful slide in the fundamental neural network lecture, but the limitation of time, I'm not going into that. So activation function has a limitation called saturation, right? So if you see the sigmoid and the tan H function, they have a saturation. So saturation means that your outcome is not changing based on your input. And that is a very difficult proposition for optimizers, because optimizer has to understand whether the change in input goes towards the minimization of the error or maximization of the error. Accordingly, it will change in input. But what happens in these activation functions is that the change in the input doesn't change the outcome. So the change in the input, there's a weight multiplied by the input, will not change the error value. And then the optimizer becomes confused. So that's why in the deep network, sigmoid and tan H functions are not used so commonly. So what the ReLU does, ReLU has always a slope. ReLU doesn't saturate. So if you change the value, either the outcome will be increased or outcome will be decreased. And that will influence the error. So you know that change in the input, that is the weight, because you can only change the weight, not the input value. So the change in the weight will ultimately move it towards the minimization, or it will move away from the minimization. And that is good for the ReLU activation function. But the functions which saturates, you cannot have that. And that's called the vanishing gradient problem. So normally we take a ReLU, and in the negative cycle, ReLU doesn't have any slope. So we take the leaky ReLU, which has a slope in the negative axis also, so the slope is much lower than the positive axis. So it's positive half. So you still can take away with the vanishing gradient problem in the negative half also in the case of leaky ReLU. So these are some sort of choices you have for the activation function. Right? Are you satisfied with my answer?
Yes, sir. Thank you so much, sir.
Okay.
We have last question from Alim Sheikh. Please highlight on overfitting in deep nets.
Okay. So overfitting is a problem where you are trying to follow exactly your training data. Now the problem is that your network parameters are so tight adjusted that it does a very good results for your training data. That's very good. But the problem is that your test data or your actual data will always vary from your training data. The problem is that as you have tightly fitted the training data, your error for the test data will be pretty high, many of the cases, because your network is tightly fitted on the training data. That's why we do regularization and dropouts in a network, just to forcefully give some errors. Okay, in the so the training result, training data, so network will not exactly give 100%, okay, 0% error for your training data, and we keep that, right? So that the test data, which is always a variation from the training data, will still get accommodated in my network and will still give an appreciable outcome. So overfitting is a very large problem in the case of networks. Okay, if you don't handle it with the case of regularization. Regularization means that you try to use dropout or regularization so that you can actually have that was an appreciable response both for the training and for the test. If you are doing overfitting, your response is very high for the training, but you are not sure what will happen in the test. Okay. Okay. How many layer I've already said, Debashish. If you see my discussion, I said that if you are only trying to understand that what is the disease condition, you stop there. But if you want to extend that, not disease condition but length of stay in the hospital is your inference, then after disease condition you again need to take one layer which will take a weighted combinations of disease condition and will tell that, hey, this is the hospital stay duration. Okay, so how far you are stretching the inference, that's basis on that you take the number of layers.
I hope we are done with the questions. So that was a very enlightening talk. Thank you so much, sir, on behalf of the organizing committee. And we are proud to have you with us. So in future also we'll be contacting you.
Sure.
Our students may contact you through email, sure, if they have any query. And for the participants, I want to inform you that this event was live streamed on YouTube. So we have the recorded version over there that you can go watch it again and again, and that may clear your doubts, I think, if you repeatedly watch the video. So thank you once again, sir. And over to you, Millie Ghosh, if you have any announcement to make, because this is the last station.
So we have. Thank you, sir. Thank you, Professor Chakrabarti. We are hoping to have you with us in your future endeavors too. And now for the participants, the feedback link, the feedback form link is already available in the chat box. Please fill up that and submit as soon as possible. And now we have come to an end of our 3-day webinar. I would request our head of the department, Mr. Dr. Sharat Sinha, to convey his vote of thanks to the audience. Thank you. Over to you, sir.
So we have had 3 days of brainstorming sessions, and unfortunately in the inaugural session, our VC sir and Professor from other departments couldn't join, but we were lucky to have our Dean sir, Professor Subhash Chandra Rai, who inaugurated the session. And I want to first thank the university authority for granting us permission to hold this webinar within a very short notice. And also all the speakers who accepted our request and lent their valuable time and shared the knowledge with us. So first of all, I want to thank all the university officials who are involved in letting us this happen. And first of all, I want to thank the colleagues, my colleagues from the CIRM, who helped us a lot in setting up all the devices for live streaming, recording, and this video conferencing. And my departmental colleagues, members of the organizing committee, who worked hard, be it for a few days, but for their contribution, the event could take place. And also all other members of the organizing committee, especially our collaborators, IEEE CIS, Kolkata chapter, and Computer Society of India, Siliguri chapter, without whose collaboration this could not have happened. Now, I would like to thank Narayan Sao, founder and CEO of Neo4 Technologies LLP Pune, for giving his beautiful talk on cloud computing with AWS. Dr. Susan Kumar Saha, Associate Professor, Department of Computer Science and Engineering, BIT Mesra, for his talk on automatic question generation and evaluation. Dr. Diptendu Sinha Roy, Associate Professor, Department of Computer Science and Engineering, NIT Meghalaya, for his talk on distributed computing practices in the IoT era. And Dr. Sheikh Muhammad Obaidullah, Associate Professor, Department of Computer Science and Engineering, Aliyah University, for his talk on behavioral biometric applications, a multilingual perspective. Dr. Sansani Aufan Wiryakul, Associate Professor, Department of Computer Engineering, Chiang Mai University, Thailand, for her interesting topic on fuzzy set theory in data analysis. And we just had Professor Amlan Chakrabarti, Professor and Director A.K. Chaudhary, School of IT, University of Calcutta, for his talk on deep network techniques for computers. Thank you, sir, so much. Actually, this is not my area of interest, but still I gain a lot of knowledge, and rather this lecture generated some lot of interest within me. So in future, I think I may go for it also. So and you have
Thanks, Professor.
motivated,
Thanks.
rather you have motivated me a lot. I may be learning some of your areas very soon, I think. So I want to thank our working president, Dr. Ardindu Mandal, who worked from day one, from the conception of the program till the end, and my other colleagues of the department, Dr. Saurabh Das, Dr. Rakesh Kumar Mandal, Dr. Mukta Majumdar, Dr. Anil Tudu, Mr. JKM Saddiq Ujjaman, Mr. Mohammad Aziz, Dr. Mili Ghosh, for the contribution and hard work to make this happen. And if I have forgotten anyone to mention over here, I beg your pardon. And I want to once again express my deep sense of gratitude, whoever has been involved in making this event happen. Not only happen, it was a successful event, I must say. Thank you once again. Over to you, Dr. Mili Ghosh.
So thank you everyone for making this webinar so successful. I would request all the participants to please submit your feedback form as soon as possible. And thanks to all the dignitaries, all the participants, all my colleagues, my seniors, and the students and research scholars of the Department of Computer Science and Applications.
Ma'am, can you please share the feedback form once again? I'm not getting it.
Okay, sir.
Okay, so thank you all. Thanks to the organizers. I have to leave the session. Okay,
Okay, so
thanks. Thanks for this organization, and I will be very happy to join you in some later event. Thank you all.
You are
Thank
most
you so much,
welcome, sir. Thank you, sir. Bye-bye, sir.
Thank you. Thank you. Bye. Bye.
Bye, sir.
And for your information, all the students and scholars, we will be sharing the form in your respective group also, WhatsApp group also. Please follow.
So thanks to all of you. Have a great day and have a great future. Stay safe. Thank you.